All right, if I were to solve this indefinite integral, it's indefinite because I don't have any upper or lower limits. What do we get when I solve this indefinite integral, Anna?
X squared over 2.
Is that all I get?
Plus C.
Plus C. Notice when we have an indefinite integral, we get a family of curves. That plus C tells me there's a lot of solutions for that. When we have a definite integral, that means we've got a lower and an upper limit. When we have a definite integral, we get a number. That's the major difference between an indefinite integral and a definite integral. When we have a definite integral, we're going from some number to some number. This will give us an actual number and not a family of curves.
Oh, the upper one is indefinite.
This one is indefinite.
Got it.
That just gives us a family of curves, a general solution, but this gives us the bottom one, the definite integral, gives us a specific number. And we saw from that worksheet, the definition of this definite integral is equal to the limit as the number of intervals, whatever, approaches infinity, and the width of each one approaches 0, of the sum from I equals 1 to n of f of x dx. That's just a definition for a definite integral. If you could find the sum of the area under the curve, you can get the value of the definite integral. And what we've looked at so far, we could actually calculate those areas. It was some kind of function that we could figure out what the area under the curve was. So we're going to look some more at that today before we look at a different way that we can find out what that is without having to look at the area under the curve. But if a function is continuous, this is one of those theorems that says that if a function is continuous on a closed interval, and I'm just going to say on closed interval AB, then the function is integrable. You can integrate it.
That's awesome.
Okay. So it's just good to know if your function is continuous, then it's integrable. And that's important because you could have a problem where they tell you this is a continuous function. So you know you can find an antiderivative for that continuous function.
So wait, if the function is, so that's meaning like the derivative is continuous, then you can find its original function?
Yes.
Okay.
Yes, that's what that means. Okay, so we have already seen from what we did on Wednesday and what we just did, if we have the integral from 2 to 5, and let's say it's just 3 dx, how did we find the value of that integral?
Find the area.
We could find the area under the curve if we were to graph it. Y equals 3 just looks like this. And if we are going from 2 to 5, we're looking at the area of that rectangle, which is 3 times 3, or 9. But we also had a property on that worksheet that said we could take 3 times 5 minus 2 if you don't want to graph it each time. So 3 times 5 minus 2 is also 9. We see it visually, and we can see it by looking at the rule. So that is a constant. If you have a constant times dx, and it's a definite integral, you can subtract the lower limit from the upper limit and multiply by the constant. In this case, 3 times 3. So that can save you some time. We also saw, and I know some of this is repeat, but I think sometimes it helps us to repeat what we've already done. If we have from 0 to 3 of x plus 2 times dx, well, we can graph that. And I'm just going to graph it as is. If you want to separate it, you can separate it into 2 integrals. The integral from 0 to 3 of x plus the integral from 0 to 3 of 2. But let's just graph x plus 2. Because it won't hurt us to get some practice at looking at these. We're going from 0 to 3. X plus 2 starts here. We go up 1 over 1. Up 1 over 1, and up 1 over 1. So here we have that area, and we're looking for that particular area. Now, I've already said you can separate that into a rectangle and a triangle, or we can use the trapezoidal rule. We need to know how to use the trapezoidal rule. Sometimes I have seen questions where they ask you to evaluate the area under the curve using a trapezoidal sum. So we need to know how to use it. The area of a trapezoid is half, in this case I'm going to call it the width, times the sum of the heights. Because that's what it looks like to us in this orientation, is a height and not a base. Okay, technically those are bases. But to find this area, we're going to have half. What's the width here? 3. And height 1 is 5 plus 2. So that's going to give us 3/2, well, times 10. No, 10. Where did I get 10? Sorry. Got 10 on the brain. 7. So 21/2, which is 10.5. All right, we've already done several with semicircles. Are we okay there?
Yes.
One more? Okay, hopefully by now you're starting to recognize the equation of a semicircle. So it's going to be a square root, so let's go from -4 to 4, twice the square root of 16 minus x squared dx. Now we've seen a rule that says we can move this 2 to the front. We just don't want to forget it. So if we draw the graph of that, what's the radius of that semicircle? 4. So it'll look something like that. And since we're going from -4 to 4, this is going to be twice 1/2 pi r squared, which we already have there. So that's going to be 16 pi. But it's twice that. Semicircle, the area of a circle is pi r squared, so half of that is 1/2 pi r squared, and then we can't forget this 2 that's in the front.
You want to half it, obviously, because it's a semicircle.
Right, and which I missed, and Emily so kindly pointed out on the one you had on your worksheet, it went from 0 to 3, and our radius was 3, so it was 1/4 instead of 1/2. All right. It wasn't -3 to +3. It was 0 to 3 on one of those on your homework. Okay, let's look at a rule. I don't think we talked about this one the other day. It's a property of a definite integral. If you're going from a to a of f of x dx, what do you think that might be? It's just a point. So is there any movement? No. So this is 0. All right. We also mentioned on the board, but I'll put it here too, if we have a to b of f of x dx, that's the same as the opposite of from b to a, f of x dx. Sometimes that's very helpful for us to know that property.
Wait, what is it AB? Is it AB?
Yes, thank you. Oh, you know what? The B was there. The A was from the previous one. The B was here. All right, so if you're going positive direction from A to B, 1 to 6, and the areas above the curve, you're going to get a positive value. But if you went from 6 to 1, it would be a negative value. Let's think about this function, or this integral. If we do from pi over 2 to pi over 2 of the cosine of x dx, what's that equal to? 0. That one's easy. Okay, now the cosine is defined at pi over 2, so we can do that. I think we did this one. If we did we work this one out? I think we did. What did we get when we evaluated that? We got this is 10.5. So if we took the opposite of 3 to 0 of x plus 2 dx, that's going to be equal to a negative. I'm sorry, that's not what I want to do. It would be 10.5. So if we did this, it would be negative 10.5. Sorry. It would go back to positive again. Yes. Yes. Yes.
Okay, so not only does this make it
All right, we also have a property that says if you go from a to b of f of x dx, that is the same as if we go from a to c of f of x dx plus c to b of f of x dx. In other words, you may have to make a change somewhere in the middle. These two have to match for that to be a true statement. It doesn't have to be, but usually it is. So let's look at an example where that would happen. Get these out of the way. All right, if I take the integral from -1 to 1 of the absolute value of x dx, let's think about what that looks like. What kind of a function is that? Okay, it's v. This is the function. I'm not looking about the derivative of the function. The derivative of that function would be like this, remember. But this, if I go from -1 to 1, it's going to look like that. So what happens to the slopes there? They change, don't they? Where do they change? At 0. All right, so we could do this visually with no trouble at all. We're gonna have to separate this from -1 to 0. Now, what's the slope? What function do we have from -1 to 0? From -1 to 0, this is the function. What's that function? Negative x. And then we go from 0 to 1, and what is our function? X.
Did we just make this up?
No, look at the function. No, look. That's y equals x right there, right?
So 0 is the c.
Yes, 0 is a c. But that's where it changes. That's where the slope changes.
Okay.
Because this is a negative x, and this is a positive x.
That's why we're using negative x.
Yes,
Got it.
yes. Which will come into play when we actually use some of the rules. But that's what happens. That's why, because the slope changed at 0. We had to change what we were looking at. Okay, so what's this area? On the left.
How does it go?
It is, well, if we're going from -1 to 0, this is 1/2. And this is 1/2. So we get 1/2 plus 1/2, so that area is 1. So the value from -1 to 1 of the absolute value of x is 1. We're going to see when we do the fundamental theorem of calculus, if we don't break that up, you're going to end up with 0. So we have to break it up at where the slope changes.
This right there you showed us.
My definite integral here. And I am going to give us that from 1 to 3 of x squared dx is equal to 26/3. Just giving you that information, 26/3. And from 1 to 3 of x dx is equal to 4. And also from 1 to 3 of dx is equal to 2. So let's evaluate that integral that I started with. I'll rewrite it down here. We can separate, and we have that x squared. I could separate this into 1 to 3 of negative x squared dx plus, and I'm going to put the 4 out front, 1 to 3 x dx minus 3 from 1 to 3 dx. Right. What did we say x squared was? From 1 to 3. Okay, and this negative makes it a negative 26/3. Plus 4 times 4 minus 3 times 2.
So minus 6.
Mm-hmm. So this is going to be equal to negative 20. Oh, don't do that. Plus 10, which is 30/3, so this equals to 4/3. All right, I think that on page 272, 15 to 45 every third, and 61 to 66. You have a test next Thursday.